Today we're going to talk about the conservation of momentum. So normally when I do this lecture, I'll go more in depth with a story about this incident. I'm not going to go as deep in here, but if you'd like to watch the video, you can. Essentially, when I was at Texas A&M, there was this incident where at A&M there's this. Our mascot is called Reveille. She's a dog. She's a rough collie. And she sits on the sideline at every football game. She's our mascot. She's the queen of Aggieland. In one football game, a football player was he was going for a pass, I think, and then I think he missed the pass or whatever, and he was running off the sidelines. This happens a lot in football. You know, they'll be going really, really fast into the sidelines. But in this case, he was running straight for Reveille. He's straight for the dog, and Reveille just sits on a blanket like on the side. And so Reveille has no way of knowing that she's in danger of this huge football player coming straight towards her. And so there's a cadet there that realizes that, hey, this dog is coming towards her. I need to protect her. And so he gets his body in front of the guy and pushes his body to the side. Now, it's important that he didn't go straight at the football player. Because imagine, you're a small dude, no gears, no pads on or anything, and you try to stop this big football player that's coming straight at you. You're going to go down too. But because he hit him at an angle, he was able to change the momentum of the football player to avoid Reveille. It's a cool video. It's interesting. I would go more in depth if I wasn't just doing an online lecture where I can't watch the video with you. But if you want to watch this video, you can watch it too. It's a little news report of the actual incident. Thankfully, Reveille was totally safe because a cadet saved her, and the cadet got a bunch of special awards. And it was cool because I was there, and the cadet was in my class at the time, and so it was cool to see everybody congrat him the day after. But conservation momentum. Here's the actual notes. Conservation momentum. It only exists when you have an isolated system. Okay, so if we have these masses where we're ignoring all the outside forces, or there are no, all the outside forces are balanced, we know that the total amount of momentum in a system must remain constant. Okay, so if all the outside forces are balanced, the sum of the forces, the net force on our system is 0, the total amount of momentum in the system must remain constant. Okay. In essence, and for you guys, this should mean two things, okay? This should mean that the total amount of momentum before a collision is equal to the total amount of momentum afterwards. This should bring back energy vibes, okay? Remember when we looked at all the energy we had before and then all the energy we had after in a two-part sequence, and they were equal? Same idea here. We have some sort of collision. Before the collision, we're going to have masses with velocities, so we have momentums, and then afterwards we're going to have masses with velocities, and we're going to have momentums, and the total amount of momentum before should equal the total amount of momentum afterwards. Additionally, in a two-body collision specifically, the impulse of one mass will be equal and opposite to the impulse of another. And so if I have a car that hits another car straight on, right, and then they deflect off each other or something, and they end up going at different velocities, the amount of change in momentum of the first car, so however much the mass changes its velocity, has to be equal and opposite to the amount the other car changes its mass and velocity. They have to be equal and opposite. Okay. Delta P of one is equal to negative delta P of the other. There's another way of writing that. Okay. And then this one is the sum of the momentums of 4 is equal to the sum of the momentums afterwards. So that's different ways of writing it with an equation. Beyond that, we really have there's no more equations, there's no more definitions today. We're just talking about this concept, this law, conservation of momentum. This is a law based on Newton laws. So let's see how we would actually tackle a problem like this. Let's say we have a ball of mass 5 and it's thrown to the right at 6 meters per second. We also have a ball of mass 3 and it's thrown to the left towards the other ball at 4 meters per second. Afterwards, the 5 kilogram mass bounces back at 5 meters per second. Where's the velocity of the 3 kilogram ball? So let's draw a picture. we have a ball. That's fine. We have a ball of mass 5, and it's traveling to the right at 6 meters per second. And then we have a ball of mass 3, it's thrown to the left at 4 meters per second. Afterwards, the 5 kilogram ball bounces back at 5 meters per second. What is the final velocity of the 3 kilogram ball? Sorry about that. So we're looking for the v backwards. So there's two ways we can tackle this. Let's first start with the conservation of energy so that the total momentum before is equal to the total momentum afterwards. And so let's see what momentums do we have before. Well, we have p of ball 5 and we have p of ball 3. They both have momentums before the collision. And then afterwards, they also both have momentums. Keep in mind, these are different things. So P5 here is not the same as P5 here. It's the before and after. So let's write before up above and make it clear, and this is after. Okay. P5 before is 5 times its velocity, which is 6, right? If you need to remember, P is equal to m times v. So our mass was 5 and our velocity is 6. The other mass is mass 3, but its velocity is -4. Remember, we have to keep that negative sign because it's going to the left. Signs matter. Direction matters. Okay? Afterwards, the 5 ball is moving at -5 meters per second. It's now moving to the left at 5, and so we got to keep that negative sign in there. And ball 3 has a mass of 3, and it has a velocity that we don't know. We're solving for that velocity. But this is just a simple equation. We can solve this, right? This is not too complex. Let's simplify this. We get 30 minus 12 is equal to -25 plus 3v. So that gives us 18 is equal to -25 plus 3v. 18 plus 25, put into your calculator if you don't know, you can get 43 equals 3v. And then we can divide by 3, and we get the velocity of the mass 3 ball afterwards is 14.3 meters per second. We could also, and let's go ahead and practice it, we could also solve this using the other definition, or the other thing we got from that. The change of momentum of the first ball is equal to the negative change of the second ball. So how does the first ball change? Well, the first ball has a mass of 5, and it has a change in velocity of Vf minus V naught, right? What's its V final? Well, its V final, we said, was -5, and its V naught was 5. It was moving to, or 6, I mean. Let's actually do this in steps. Hold on. I think I'm going a little too fast here. Definition of change of momentum, we remember, is mass times the change in velocity. Whoops. Here we go. It's mass times the change in velocity. And this is of the first ball. And the negative mass of the second ball times the change in velocity of the second ball. So this is the 5 ball times the change in velocity of the first ball, of the 5 ball. Well, we know beforehand the 5 ball is moving to the right at 6, and then afterwards it bounces back at 5. And so afterwards, the final velocity is -5, and before, the velocity is 6. So -5 minus 6. Final minus initial, Vf minus V naught. And this is equal to the -3 ball times, again, final minus initial. We're looking for the final, and the initial was left at 4, so minus -4. Okay? And then we can go ahead and simplify. We get -55, and then we need to distribute this -3. We get -3v minus 12. So -55 plus 12, we get -43 equals -3v. And you can see how similar these equations are. We hit it with a negative sign, we get 43 equals 3v, and it's the same equation. We're going to get the same answer. There's a different way of solving the exact same problem. Whichever way makes more sense to you is an adequate way to solve these problems. Let's try another one. A 75 kilogram football player runs at 10 meters per second and tackles a 95 football player running at him. Afterwards, they move together at 2 meters per second. How fast was the heavier player moving initially? So I have one player, 75, moves at 10 meters per second. And then there's a 95 kilogram player running at some velocity v. And then afterwards, they both move together at 2 meters per second. They both are moving this way at 2. How fast was the heavier player moving initially? So we have this. We have, let's go ahead and do the first way, where we had the sum of the momentums initially is equal to the sum of the momentums afterwards. So beforehand, we have two bodies. We have the 75 kilogram guy, and he's traveling at 10 meters per second. And then we add the second guy. The second guy is 95, and he's traveling at some velocity. Yes, I know what you're thinking. He's probably traveling to the left, and so that v is going to be negative. The math will work itself out. We're going to get a negative answer. So we can just go ahead and add them. Afterwards, they move together at 2. So there's two ways to think about this. We can just go ahead and do a 75. We know each one is moving at 2, so we can do them separately. 75 times 2 plus 95 times 2, because they're both moving at 2. Right? So we add both their momentums, where both their velocities is 2. But additionally, this is the same thing as just saying having them as one mass. If they're moving together, they're essentially one mass. And so instead, we could just add their masses together and multiply by their velocity. And then there's just one momentum afterwards, right? N times v, where m is the sum of the masses because they're moving together. Whichever way you like, you get the same number on the right side. And so on the right side, you should either way get 340, whichever way you like to write it. Over here, you get 750. And then we're looking for v. So let's go ahead and subtract 750 from each side. 95 times v is equal to negative 410. And then we're going to divide by 95, and we get a velocity of negative 4.32 meters per second. And again, that makes sense because the football player is running at him, and so it should have been negative, and so this works out. So that's all the practice. They're really not any more complicated than that. It's just, you just got to practice. If you want to, I can go ahead and I'll write the equation here. This is a cool video. It has to do with momentum and energy and a couple other things. If you want to watch it, it's a pretty cool video. It's by, what's her face? Physics Girl? Is that what her name is? Yeah, Physics Girl. So it's a cool video that I like. If you really need an equation for this, I will write it for you. But I try to discourage thinking about an equation for momentum, concentration momentum. You should just think about the momentum, the total momentum before equals the total momentum afterwards. But if you really need an equation, you can do mass 1 v1 initial plus mass 2 v2 initial equals mass 1 v1 final plus mass 2 v2 final. Again, this is just the sum of the momentums before and then the sum of the momentums afterwards. Right, it's the same exact thing. I'm just plugging in what that means. It means momentum 1 initial plus momentum 2 initial is equal to momentum 1 final plus momentum 2 final. And then I'm plugging in mv for both of those momentums. So I'm just kind of expanding it out for you. If this helps you solve these problems, go for it. On the homework, if you ever need to solve for mass, which I think is a couple problems on there, you need to factor. So in those cases, you either need to combine like terms. You really just think about combining like terms. You're going to work on combining like terms. So plug in your numbers, and if you're solving for like M1, maybe you need to move all the M1s to the left side and then combine like terms. Everything multiplied by M1 is like terms, and so you can just add the coefficients. So if you had like M1 V naught 1 naught, or if you had like, you're solving for M1 times 2 equal to M1 times 4 plus 10 or something, you can move the M1s to one side. And then you can combine like terms by adding the coefficients. Here's the coefficient here, here's the coefficient here, but you subtracted them, and so you're going to do M1 minus 2. So we have, because we have a 2 minus, or plus a negative 4. Okay. With that, I have nothing else for you, so you can complete the homework now. Have a good day.